welcome to the 22nd Annual Benjamin I. Wheeler Society Tea. This is the group that honors and recognizes those of you who have included us, Cal, in your estate plan, your will, your trust, or a charitable gift annuity, charitable remainder trust, and many other options that we're always happy to talk with you. I think it's now dark out there, so you probably can't see my colleagues. I want to welcome you on behalf of the other fundraisers in the Office of Gift Planning, who are somewhere out there. Amanto Marcatulli and Randy Silverman. I know I see her over on I think it's stage, is it stage right? I always get baseball and staging confused. Ed Edwin is over there, and then Carrie Fuller. Where are you, Carrie? Oh, she's over here. So we want to welcome you to this event. And welcome you also, I know a number of you said you had not been in the Zellerbach Playhouse, so I want to welcome you to this venue. It's actually 40 years old. And when the hall went up, this was put in. It's the home, I gotta make sure I say this correctly, of the Theater, Dance, and Performance Studies Department, which has a history going back to 1870, 2 years after the founding in one form or another. And it really is one of the most distinguished dramatic arts departments in the country, often ranked right up there with Yale and some other dramatic art schools. And the one thing I wanted to say about the Playhouse is it hadn't been renovated in the 40 years, the first 40 years. We're now in the year 41. And we were very fortunate in that a couple of the donors left some undesignated bequests to the campus. And at a time when Yale and Harvard and other endowments were skyrocketing and they were trying to raid all of our professors, this department was threatened, as were many, but fortunately the bequests were able to be used to upgrade the lighting and the sound system and all the other things that are needed to keep a modern performance arts department going. So we appreciate all of your estate gifts. Appreciate even more if you might consider maybe adding at least a portion unrestricted, because there are those times when something like that goes an awful long way. So without further ado, I'm going to introduce this afternoon's speaker, Professor Richard Muller, who earned his PhD here at Cal in 1969, and he studied under Nobel laureate Luis Alvarez. He's been on the faculty since 1978, and he's also a senior scientist at the Lawrence Berkeley Laboratory, where he's associated with the Institute for Nuclear and Particle Astrophysics. He has a very distinguished honor as being the only full professor on the Cal campus who was arrested during the free speech movement in 1964. So definitely there's probably a pre-64 view of that and a post-64 view of that, so I'll let the professor handle all those. He is a winner of Berkeley's Distinguished Teaching Award, teaching a renowned course for non-scientists, Physics for Future Presidents, which was voted best class at Berkeley in the Daily Californian's annual Best of Berkeley. And he recently published, which is right in front of me. I'm sure he'll plug it too. I feel like I'm on Oprah or something, but here it is for lay people like ourselves. And he is a fellow of the American Physical Society and the American Academy of Arts and Sciences and past winner of the MacArthur Fellowship. So please welcome Professor Muller.
I have to say that when I was arrested in the free speech movement, the last thing I ever imagined was that someday it would be listed among my honors. That was actually my most recent honor is appearing here before you. This is an honor. I'm glad to be able to do it. Unrestricted funds, oh God, have they helped me a lot. My career has been in working in areas that are usually not along the lines of the previous workers, and finding money that can be used for that. It's worth, in my research, it's worth 5 times as much as money I get from the government. So I want to thank you for that. This is also my opportunity in talking to you today to pay back the university for having been so wonderful to me over my career. So I'm really pleased to be able to do this. The topic today is physics for future current presidents, the things you need to know, I was inspired in this several years ago. It's not just presidents, it's also congressmen, but hey, aim for the top. And it's the things that so many people are proud of not understanding physics. I mean, someone will be criticized, a president will be criticized if he doesn't know the difference between Shiite and Sunni. And yet, the difference between a plutonium bomb and a uranium bomb and a dirty bomb, oh, you don't need to know that. I'll tell you another little story. I have my students read the newspapers every week, and I expect them to report on technical articles. And many of the students found this a revelation. They said to me, I didn't know I was supposed to read those articles. I didn't know they were for me. I told this story to a bunch of professors. I hosted a physics department lunch, and they laughed. And I said, okay, to the physics professors, how many of you read the financial pages this morning? And they kind of looked around, and you could see them thinking, wait, those pages aren't for me. So we each have our gaps, but if you're going to run the world, you need to know things. And particularly in a high-tech world, where so many decisions have high-tech components to it. Things like global warming, nuclear weapons, all these things have high-tech components. And I believe that when the average student, the liberal arts student, the pre-law, pre-business student doesn't know these things, it's not their fault. It's because they're badly taught. And I'm going to go through the entire course in the next 45 minutes. In fact, let me get this, my timer going so there'll be time for questions. Click that. I'm going to go through the whole course. And at some points, needless to say, even though you are the brightest of the brightest, it'll be a little bit fast for you, so don't worry about that. Mostly I want you to know that all this technology material, this stuff, you can really understand. An important thing is it has nothing to do with the math. The math is what you need. It's like being an architect and you may not be really good at putting in 80 nails per minute, but you know there are people who can do that. Well, there are people who can do the math, and if you guys ever need to work a calculation, just hire a physicist. But you need to understand it. So what are we going to cover today? Not everything in the course, but I'm going to cover these things. A little bit about terrorism. Yes, the physics of terrorism and counterterrorism. That's one of the key things we discussed. Nuclear weapons, nukes. What's going on there? Energy, obviously important, and climate change. So these are the topics I want to give you the quick brush through today. Let's start with terrorism. What do we worry about for terrorism? What's in the newspapers for terrorism? Well, obviously, nukes. Just wishing I had a portable mic at this point so I could walk over there. What is it? Let me give you a quick course in nuclear bombs. And again, I'll go too fast for you to get everything. Don't try to take notes. I'm going too fast. But listen to it and get the sense of what I'm saying. There'll be nothing here that isn't easily understood. I'm just going to go too fast for you to remember it all. So let's talk. There are three kinds of nuclear bombs. Actually, there are 17 or 24, depending on how you count. Just like there are so many different kinds of snow for Eskimos. The experts know these different kinds. But generally speaking, there are three kinds, and you need to know these. Most people think there are two. There's the atomic bomb and there's the hydrogen bomb. But the atomic bomb comes in two kinds. There's the uranium bomb and the plutonium bomb. You've heard of uranium and plutonium. Those are actually very different kinds of bombs. Those are used in a hydrogen bomb to trigger the explosion of the hydrogen. So if you're going to have a hydrogen bomb, you have to have an atomic bomb, which is either uranium or plutonium, to set it off. If you're going to be a terrorist or a rogue state or something like that, then you need to develop the atomic bombs, which is either uranium or plutonium. So let's talk about those. Uranium bombs are made out of a minor constituent of uranium. It's less than 1%. 0.7% of uranium is uranium-235. Because it's uranium, you can't separate it chemically. So you need some advanced technique, and this is very difficult to do. In World War II, Lawrence of Berkeley, the great scientist from whom the Lawrence Berkeley Laboratory is named, came up with a way of doing it. You would take the uranium, you would vaporize it, you would put a charge on it, and you'd send it through a magnet. And the uranium-235 would curve in that magnetic field. The uranium-238, because it was heavy, it didn't curve so much. It would land on a plate. At the end of the day, you'd scrape off a little bit of uranium-235 and then do it again. And after a year, they had enough uranium for one bomb. It was 1945. They couldn't afford to test it and wait another year. So they dropped it on Hiroshima. My thesis advisor, Louis Alvarez, was on the chase plane. His job was to measure the size of the blast. This was what we used to destroy the city and people of Hiroshima. Once they had separated the uranium, they never tested this bomb, but they were pretty sure it was going to work. The reason is uranium is easy to make a bomb. This is what gives rise to the belief that a high school student could make a bomb. It's because if they have the purified uranium, which is very hard to get, imagine the big magnets and so on, scraping it off, very difficult. If you have that material, then a gun design works. It's really a cannon. You take two pieces and slam them together. Each one is less than a critical mass. They come together. They're more than a critical mass. You have the explosion. This is important because it was never tested, and this is the kind of bomb that Saddam was designing. Saddam's bomb. At this point, I usually lose all credibility. Everybody says, doesn't he know Saddam didn't have a bomb? We'll get back to that in a moment, but it's actually, you're confusing the first Gulf War with the second Gulf War. It was the end of the second Gulf War that we learned that Saddam didn't have a bomb then. But after the first Gulf War, he had a bomb program. It was dismantled by the United Nations. I'll show you the photo. A plutonium bomb is something quite different. I could also use my super laser here, but it's a little bit too bright. The plutonium bomb, plutonium doesn't exist in nature except in tiny amounts. Plutonium is something we manufacture in a nuclear reactor. Anybody who owns a nuclear reactor can extract the plutonium. Many countries around the world do have nuclear reactors. A nuclear reactor manufactures plutonium. It takes the uranium-238, that 99% that's useless for a bomb, and turns it into plutonium. And then you can chemically separate it. That's called reprocessing. This is what North Korea has been doing. They have a nuclear reactor. The plutonium is building up inside. Once there's enough plutonium inside, they say, oh, you've insulted us, no more inspections. Then they take the plutonium out chemically, and they make a bomb. The problem with the plutonium bomb is the gun design doesn't work. You need an implosion, like squeezing a water balloon, but you have to get it perfect or it'll squeak out between your fingers. Very hard to do. We had plutonium in World War II. I was a kid at the time, weren't sure, we, the US, weren't sure it would work. And so there was a test at Alamogordo. That was, in fact, the first nuclear explosion. Alamogordo, 20,000 tons of TNT equivalent from about 12 pounds of plutonium. That plutonium, oops, I slipped ahead by accidentally pushing the button. That plutonium will fit in a coffee mug. And that was the bomb of Hiroshima, 18,000 tons of TNT. But it's implosion, very hard to do. This is the direction North Korea has been going. And they have now exploded 2 nuclear explosions using plutonium, which they got from their reactor once they decided that we should not have inspections. They did that. Getting back to Saddam. Saddam, after the first Gulf War, you remember, we did not go into Baghdad, but the UN did. And we had complete inspections in Baghdad, and they found Saddam's program. Nobody denies this. This is not a controversial issue. The UN report said he was making a bomb. He had enriched it from 0.7%, less than 1%, up to 35% of uranium. That's the hard part. After that, you mostly don't have much material left. It's easy to go beyond that. 35%. The device he had used, we had been looking in the intelligence community, and in my introduction, I've actually spent 35 years working on national security issues for the US government during my summers. And we had been looking for their nuclear program, and we didn't find anything. We were looking for modern methods of uranium purification. We were looking for centrifuges, which is what North Korea, what Iran is using. We'd been looking for other technologies for diffusion plants, and Saddam surprised us. When the UN went in, what he found were calutrons. Calutrons, that's what Lawrence used in World War II. They were never used again. After World War II, we had more modern methods. We weren't looking for the calutrons. By the way, the calutron got its name because Lawrence, who was here at the University of California, this beam goes in a big thing like that. The uranium-235 goes in a smaller circle. The uranium-238 goes in a big one. His big device looked like a big letter C. He named it after our university, Cal. It's a Calutron. You know, for some reason, when you get the student tours, they never mention that the bomb that destroyed Hiroshima was created thanks to something that was named after UC. That's not part of the standard tour. But think about Iran now for a moment. Iran is using centrifuges. This is where you get a tube, you put in the gas, you spin it really fast. The heavier uranium-235 goes to the outside. The lighter stuff is the inside. You take a straw and you pull out that lighter stuff. In this room, you could put a bunch of centrifuges and have enough uranium for a bomb in 1 year. Just in this room. It's very quiet, very little energy, very hard to find on the outside. This is what Iran is doing. Now, they say that they are purifying uranium for nuclear reactors. And that's legitimate. But the same device allows you to enrich it up to 80, 90% for a bomb. And then what kind of bomb design do you need? Our CIA says we have no evidence they're designing a bomb, but it's the gun design that doesn't need the design. It will work the first time. This gets lost sometimes. So Iran has a legitimate reason for purifying uranium. At the same time, it puts it into a position where it could make a bomb that would work without a test. So this is where a little bit of physics knowledge can help. Okay, so what about the North Korean nuke? Well, they exploded a bomb. What do we think of when we think of an atomic bomb? Let's look at New York City. That's a 1 megaton bomb. That's the damage it does. The blue is basically blasted out. The red is burned by fire. And there's debris that goes beyond that. So basically from Manhattan all the way up to the top of Central Park to the Battery is destroyed with 1 megaton bomb. These are the horrors that we grew up with, where many of you, not a few of you, are as old as I am, and remember the take cover drills and so on. I was growing in the South Bronx. I am within that circle right there. So this is the terror we remember. What about the North Korean nuke? Well, here is for the first North Korean nuke, the smaller one, this is the circle of destruction, if you can see it. That was less than a kiloton. It was 0.4 kilotons. There is the circle right there. If it's in the middle of Central Park, it wouldn't hit the Museum of Natural History on one side. It wouldn't quite reach the Metropolitan Museum of Art on the other. This is important to recognize that their first bomb was a dud. What about their second bomb? It was a little bit larger. It actually would have reached both museums. How much destruction is in that circle? How bad is it? How much energy is released? I'm now going to show you a photograph, an event with which you are all familiar, which released more energy. It's a terrorist event that released more energy than the larger, actually both of them combined, the North Korean nukes. You ready? 9/11. Surprises most people to realize how much energy was released. Well, it's not, the energy came mostly, not from the impact, which had very little impact, but from the burning of the fuel in the airplane. 2 airplanes, 120 tons of fossil fuels, each one 60 tons. Here's the remarkable number. Jet fuel or gasoline in your car has more energy per pound than TNT. We don't use TNT because it has huge energy. We have it because it doesn't require oxygen and can explode very rapidly, and that creates great forces which can crack concrete. But if you're taking a building down, all you need to do is to heat up the columns, because when the columns heat up, the molecules are bouncing faster. When they're bouncing faster, they get a little bit further apart. When they're a little bit further apart, the force between them is weaker. And so you weaken the column. Take a soda straw, put it between your hands. And you could weaken the soda straw, but easier. Just push a little bit further, and it's quite strong. It's amazingly strong when you realize how thin it is. And many of you are old enough to remember paper soda straws. Can't get them anymore, but I'd love to, because they demonstrate how well the strength of paper. But you push a little beyond their buckling strength, and boom, it goes right down. No strength whatsoever. Once it begins to bend, this is what happened in the World Trade Center. And then a second thing happened. Once that goes down like that, now you have the hammer effect. Take a hammer, put it on your hand, weighs a pound. Drop it 10 feet onto your hand, and it will be a lot more than 1 pound. The multiplication is the ratio of the distance it drops to the distance it stops in. If that's a factor of 500, then it's 500 pounds on your hand. This is what happened to the next floor. Once that first floor collapsed due to the buckling, because of the weakening of the columns, the lower floors didn't happen to be weakened because they got the hammer effect. Down, 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 almost at the speed of sound. I gave a talk of this on the American Physical Society because there's so many people going around saying, if you knew any physics, you knew that this building would not have collapsed. But I'm giving you the lecture I gave on 9/12 to my class, when I walked in and said, change of lecture today, let's talk about what happened yesterday. So we're getting into energy now. And let's talk about some of these numbers. Here's the most complicated list of numbers that you're going to see. Don't memorize these. My students all learn them because they're all so important. But I'm going to point out a few of the more interesting ones. This is the energy per gram for different materials. So everything from a bullet to uranium-235, asteroid impacts, coal, butter. This is the energy per pound, per gram. Let's compare it to TNT. The numbers I was just telling you about, TNT and gasoline. Look at that. That's 15 times more energy in a pound of gasoline than in a pound of TNT. When I look at these numbers, my conclusion, and this is what I advise the government, is okay, worry about nukes, but not disproportionately. If I were a terrorist, what I would do is bring in gasoline, the weapon you can buy at your corner station. This is what I fear. I fear that they've had success in airplanes, and they're going to do this again. They can't hijack an airplane. I told my students in 912, it's not going to be any hijacking of American airplanes in the foreseeable future. Once they lock the door, once the passengers won't let them hijack the airplane, that's no worry. What they're going to do is buy an airplane, maybe a DC-3, fill it with gasoline, and then take it into a football stadium on Sunday afternoon to be televised. This is what I worry about, not them smuggling in some North Korean nuke that may or may not go off, and if it happens to be in San Francisco Bay, will actually do very little destruction, and even the radioactivity will not be very bad from something like that. No, and Jose Padilla, who was going to spread a dirty bomb, he got a message, according to the deposition at his trial. Jose Padilla was told by al-Qaeda to give up the idea of a dirty bomb. They knew that was unworkable. Dirty bombs really don't work. I can go into that in more detail as I do in the class. Instead, they suggested that he rent apartments around the city of Chicago and have them explode using the natural gas. Fossil fuels again. Let's look at these fossil fuels. Listen, think of gasoline. Think of this amazing gasoline. 15 times the energy of TNT. Think about gasoline the way most people did, let's say 30 or 40 years ago. Some of you are old enough to remember that. And let me trigger your memory. What is gasoline? It's the ideal fuel. Unlike coal, when it's gone, it's gone. You don't have to shovel the ashes out of your car. It just disappears. Oh, does it create pollutants? No. It only creates carbon dioxide. What is carbon dioxide? That's that good gas. Same thing we breathe out. The carbon dioxide that helps plants grow. This is the view 40 years ago. Now it's the big evil thing. Most people didn't recognize the global warming potential back then. A few did. I'm sort of proud to be one of the early ones in that. And then is there a danger? I mean, nuclear power, it could melt down and release radioactivity, and that could kill thousands of people. A real danger, but gasoline doesn't have any real danger unless you include in war. And many of us believe that war in the Mideast would not be taking place if not for the fact that it's a key oil region. So it's not clean, safe, or cheap anymore. And that's important to know. What about alternatives to gasoline, like batteries? This is a key number, very important to know. Battery compared to gasoline, per pound, gasoline has 100 times the energy of our best computer batteries. 100, that's why the Tesla Roadster, how many people here own a Tesla Roadster? I'm just curious. Okay, you don't have, how many people here aspire to driving a Tesla Roadster? Did you know it has 1,100 pounds of batteries in it? It's probably heavier than the cars you drive now. That's just the batteries. If you bought them at retail at the same price that I pay for this, it'd be $135,000 just for the batteries. Of course, they get them at a discount. But battery-driven automobiles, not unless the price of batteries comes down. Plug-in hybrid, I'm not going to ask you who aspires to have a plug-in hybrid. I don't. I own a hybrid. I'm not going to plug it in. It's too expensive. Why is that? I've been saying this for years, but Consumer Reports finally came out with the numbers and published it, so I can now refer to them. And what they showed is you can convert your Prius to a plug-in hybrid for a mere $10,000 of batteries. Once you have done that, then you will, in fact, save money on gasoline for 3 years until the batteries have to be replaced, because they only last 3 years. And you, will then replace them for another $10,000 worth of batteries. But the good news is you will have saved $2,000 in gasoline in the interim. It's good for energy security, and it's good for reducing global warming. It's good, but it's very expensive. As you're going to see, I'm going to have a recurring theme that if we are going to solve the problem of global warming, if we are going to reduce the dangers of the carbon dioxide emissions, we can't do it by spending big bucks. Well, you and I can, or you can. We'll see how my salary cut, if I can still do it. But anyway, you could spend the money, but I'm going to come back to this near the end. You're going to see that most of the global warming, unfortunately, most of the global warming that is projected, this 5 to 7 to 8 degrees Fahrenheit of global warming that we all fear, most of that is going to come, in fact, unfortunately, from China and India and not from the US. And therefore, if we are real good guys and we really cut back, we hope that will serve as an example for them to cut back. If they choose not to because they can't afford it, then we'll have global warming anyway, because just a tiny fraction, maybe 10% of the global warming, less than 10% of global warming is going to come from the United States. A quarter of it has so far. But anyway, we'll get back to that theme in a moment. It's unhappy news. The price of energy is also fascinating. It's completely out of balance. We don't have an efficient economy in this. If we look at here, for the computer battery, I've put in the actual cost per kilowatt hour compared to typically for electricity, it's 10 cents, 15 cents per kilowatt hour, $2 when you include in the battery replacement cost. Batteries are under development. If we can get batteries that can be recharged 3,000 times instead of 300, if we can get the cost down and the energy density up, then batteries have a future, but not in the near term. China cannot afford the Tesla Roadster. Natural gas is out of whack, it's down. And right now, the biggest problem for people who want to push alternative energy, the biggest impediment has been the dropping price of natural gas. We can try to be noble and spend more money on alternative energy, but most people don't, and certainly in the developing world they don't. And the price of natural gas has crashed. Gasoline has built up somewhat. It's gone back up a little bit, not natural gas. And the prognosis is that it's going to stay down for a long time, largely because of new discoveries around the world. In the United States, the shale gases are keeping that price down. I was talking to some oil men recently, and they were very depressed about the future of natural gas. I said, why, are we running out? And they said, no, because the price is going to stay down. Different perspective on optimism here. Let's talk about global warming. Okay, this is a plot of the increase of carbon dioxide, usually shown with an offset 0 to make it look more dramatic, but that's a 36% rise. And what's scary about that 36% rise is back in 1896, Arrhenius calculated what would happen with increases in carbon dioxide. He was the great granddaddy of this. And he calculated, he gave us the equations. He never projected a 36% income, but he gave us the equations. You plug into his equations, and you find that a 36% increase in carbon dioxide should lead to about 1 degree Fahrenheit of global warming. Now we get to great Roger Revelle, the modern hero of global warming, professor at UC San Diego. And he inspired additional work, including the measurements I just showed you, and a report with Gordon MacDonald, who was later a co-author with me on a book on climate that we wrote together. And these numbers, it turned out, after all this enormous work and big computers and doing things in a more sophisticated way, what this group concluded was that a 36% increase in carbon dioxide would lead to about a 1 degree Fahrenheit rise in temperature. Okay, well, sometimes the back of the envelope is better. This report did things more carefully. It included landmass distribution and so on. Now we get the IPCC, Intergovernmental Panel on Climate Change. You don't have to remember that, but you should know the initials, IPCC. They won the Nobel Prize, the Peace Prize. You should know that. They shared it with Al Gore. They were the scientific team. He was the publicist. So their work, they used enormous computer programs, and they're constantly being criticized for these enormous, complicated computer programs. How can you trust those programs? Maybe they twiddle parameters. You know what number they get? they get a 36% increase in carbon dioxide will lead to about a 1 degree Fahrenheit rise. So this is why people love to attack them for using these elaborate calculations. The calculations are better than these calculations and are better than that calculation, in my estimation. But they all yield the same result. Yes, it's possible that they're wrong because of an issue of cloud cover. This is the way the greenhouse effect works. Sunlight comes right through the atmosphere to the ground. Some is absorbed, but not much. You can put in the details, doesn't affect the answer. The ground warms up, and then it emits heat radiation, the same thing you get from a heat radiator. It's infrared radiation. It's invisible, but you could feel it on your face. It emits that radiation, but that radiation doesn't get through the atmosphere. It absorbs and heats up the atmosphere. And then the atmosphere emits it up and down. But you'll notice the Earth is getting, it turns out, about twice as much radiation. Some of it is just radiation that's being returned. A blanket works in the same way. You don't have to have an electric blanket. Just get under it, and it will reflect some of the heat back to you, and that's good. And it's good for the Earth, because without the atmosphere, the temperature of the Earth would be below freezing over the entire Earth. Life would be impossible as we know it. But this warming keeps it above freezing, gives us an average temperature about 57 degrees Fahrenheit. Here is that temperature, plotted as a function of time. You are now seeing the global warming plot, the key plot for global warming. These are thousands of thermometers around the world. From 1850 onward, you'll see the temperature has risen. According to the IPCC, remember, UN organization, remember those letters, won the Nobel Prize, the IPCC. That's the consensus that everybody refers to. It's the IPCC, a big report every 4 years or so. According to the IPCC, the warming that took place up to 1957 may have been natural because the solar activity had been growing. A lot of people don't know that. They say, oh, IPCC is completely untrustworthy. They don't take into account that maybe the sun is doing this. These people have never read the IPCC report. There are other people who will say all this warming is due to humans. Al Gore says that. He attributes this to humans. He's actually disagreeing with his co-winners, with the scientists who won the Nobel Prize with him. They say you can't tell whether this was due to humans or not. Probably not. It's just the solar activity. But then the IPCC says this last 1 degree is very likely, 90% probability, very likely due to human cause, mostly carbon dioxide, methane, and a few other gases. So 1 degree Fahrenheit, that's kind of scary because that agrees with Arrhenius, with McDonald, and with the predictions of all these. This is why I worry. That's just a funny coincidence that the number turns out to be about right. The solar activity at this point started leveling off and then going down a little bit. And so this is why you can't attribute that to solar activity. There's other evidence too, sea level rise. This is the sea level rise that was observed due to global warming. The first part of this was natural, and then this part here is man-made, global warming. But you'll see sea level has gone up. A lot of people, we ask how much has sea level gone up? They're a little bit surprised to find out that it's 20 centimeters, 8 inches. That's in the last, basically, 130 years. It's gone up 8 inches. How much do we project it will go up in the next 100 years? Well, I'll show you the data later if I have time. IPCC has done this projection. It turns out to be about 1 or 2 feet more due to global warming. Many people look at the movie, at Inconvenient Truth, and they see New York City being flooded. But they don't listen to the way Al Gore introduced it. He says, if Greenland were to melt or Antarctica were to slide into the ocean, then sea level would rise by 100 meters, and he shows the film. And people forget the introduction. He's absolutely right. If that were to happen, we would flood a lot of New York City and other places. But the IPCC doesn't project they will melt. That's not part of, there are some scientists who say, but they could melt from the following mechanism, but that's not the consensus. The consensus is real. It's a group of very good scientists. I'm not part of it. I've reviewed some of their work, but I haven't been on that team. But it's actually very moderate, and they're not projecting all these horrific things that you see on An Inconvenient Truth. There is a problem here in California because a sea level rise of 2 feet is projected will destroy the levees in the Central Valley. That will flood the inland with seawater. and will cut off virtually all the water that goes to Southern California from the north, especially for the farming area. So probably the worst place in the world to be with 2 feet of sea level rise is in California. We are probably, you may lose a little island here and there in the Pacific, people will be moved out, but our agriculture will be devastated by that. So that's something to worry about. There's other evidence for global warming. The IPCC gives 3 main things: the temperatures, the sea level rise, and then they say the climate, the melting of ice in the north. I don't think the melting of ice in the north should be included for the very simple reason, let me skip that they also, in 2001, the IPCC asked the modelers to predict what's going to happen in Antarctica. And they took their models, I think there were 8, they all predicted the same thing, that due to global warming, the ice in Antarctica would increase. Just the opposite of what you were probably thinking. Why? Because Antarctica, even with 1 degree of global warming, is still below freezing. What's happening, though, is that the seas are warmer, more evaporation from the heat, therefore more moisture that falls in Antarctica. Every single one of those models predicted that evidence for global warming would come in the form of increased ice in Antarctica. Now, you've probably all been reading that the ice in Antarctica has been going down, 36 cubic miles per year from the satellite measurements. What you have not heard, probably, is that contradicts global warming. In fact, even the president's science advisor cited the disappearance of ice in Antarctica as evidence for global warming. And I'm sitting there saying he didn't read the reports. He got it backwards. So anyway, let me run through. Global warming is real, something that I believe we have to worry about, but I believe that instead of trying to scare you by exaggerating it, I should show you the real evidence. So let me begin, and I did. Let me now show you some of the evidence, most of which contradicts what you probably think you know, or at least what many of my friends think they know. This was one of them. Here's another thing. This is often put forth. Oh, this is often put forth as evidence for global warming. Don't believe it. I won't say a word. Just look at the slide. This is usually put forth, and it is wrong. I think this has a different cause altogether. Maybe it's a consequence of global warming. What about the increase in hurricanes? Everybody knows that hurricanes have been increasing. Well, they have been increasing, but it's very hard because we make so much better measurements now. Look at the hurricanes of 1933 and how many of them were out at the deep ocean. I'm sorry, that's here, 1933. There were none out there. Now for 2005, a large number of them were out there. Did the hurricane suddenly invade the deep ocean? No. Nobody used to go out there because it's dangerous to be that far away in the middle of a hurricane. So we didn't report any. Now we have satellites reporting them, we have automated buoys reporting them, and we include them in, and we run out of letters for the alphabet. If you really want to know whether hurricanes are increasing or not, you need to take a subsample that is unbiased. Every scientist knows this. Let's pick an area where you would never miss a single hurricane, the US coast. Those have certainly been reported since 1900. Let's look at the trend, and here they are. You can look these up in the World Almanac, or if you're younger, you can look it up online. These are the hurricanes since the beginning of the century. This is the number every decade. And you'll notice there is a significant, well, small, but it's trending downward. The number of hurricanes hitting the US coast have been decreasing. What about the intense hurricanes? Those are the red ones. Those are the categories 4 and 5. Those have been going down too. What about Katrina? People think of Katrina, this terrible Category 5 storm that destroyed this city, and there will be more Katrinas. I've heard really top scientists say there will be more Katrinas. What they're missing is that Katrina was Category 5 when it was out at sea. When it hit New Orleans, it was Category 3. It was the first hurricane to hit New Orleans since those levees had been put up, since everything. Any Category 3 hitting New Orleans would have put it below sea level. Right now, if you go back to 2000, go back before Katrina, and ask any real expert, ask the disaster agencies, what are the 2 areas of the world you are most worried about, the ones that are most likely to be damaged in the future and cause horrendous effects from natural causes? They say, well, that's easy. New Orleans and the California Delta. It's also below sea level. Okay. What about tornado? I'm making you feel good, I know. Well, what about tornadoes? Listen to an inconvenient truth. He says the number of tornadoes is going up. The U.S. government publishes a report every year. It's available online. This is their U.S. government report. This is strong to violent tornadoes, the ones that actually touch the ground, and they have been definitely going down. Can this be related to global warming? Actually, yes, it can. There are models of global warming that would predict reduced storms simply because global warming tends to warm the poles more than the equator. That's less of a temperature gradient, and therefore that's what triggers the storms. It's not the absolute temperature. It's the temperature differences. Storms are generated because of air moving from the hot equator up north. That generates hurricanes. The tornadoes have been going down. How does I've written to Al Gore, I've tried to phone him, I've tried all sorts of things. He hasn't gotten back to me. Why does he say they're going up? My best guess is that he's including all hurricanes, including those we now detect tornadoes, including those we now detect by radar. What about wildfires? It says those are going up. Well, they're going down. This one I managed to track. In his book version of his movie, he has enough references that I could find out what it was. And it turns out that when he says wildfires are going up, he's not talking about wildfires in the US, he's talking about wildfires in North America. And he's measuring them by how much damage they do. So if you build things closer to the forest and you get burned out, that counts for more. What about the warming of Alaska? That's an interesting one. Here's the data for the warming of Alaska. This is Fairbanks. Everybody knows Alaska is the canary in the cage. And and they usually draw a diagonal line through this. Although some people think they see a step. And which do you do? Well, that's not in the data. That's all in your bias. But I've managed to find some other data. This is in the North Pacific. Very good data that shows there's a step that takes place exactly at that same time. And since that time, the temperature in the North Pacific has not increased. The scientific paper that studied this, they call this a regime shift due to a change in the water flow. That's speculation, but they don't put a diagonal line through it, as most people do here. I then spoke to an expert at climate at Fairbanks. He's at the Climate Change Center. He's deeply concerned about global warming, about the warming of Alaska, about the melting of the permafrost, and so on. But he says to me, there hasn't been any warming here for 20 years. This plot shows that, and I can explain it to you in green. This is the most recent year, and this is the average. The color is the average. Alaska has been warming since 1980. It has not warmed since 1990. But these are the things that people will say. Why do they tell you that? Because they're worried about global warming, as I am, and they want to scare you. I can scare you by saying the few things that will scare Californians, like the rising sea level and the delta. And I'm deeply concerned because the projections seem to be correct. It's not the current global warming that's a problem. Here's a number. This global warming so far has been about 1 degree Fahrenheit. That's half a degree. It's actually 0.8. It's 0.4 degrees Celsius. 0.4, that's global warming. The US has contributed 1/4 of that. We're the bad guys. We contributed 0.1 Celsius of global warming. That's not enough to melt Kilimanjaro or to kill polar bears. 0.1 Celsius. Of that 0.1 Celsius, our automobiles have contributed 0.025. 0.025%. 0.025 degrees Celsius. That's 1/40th of a degree Celsius from our automobiles. The problem isn't what we have done so far, although this is what the Chinese like to draw attention to. It's not what we have done so far. It's what is coming up if we continue to expand our economy in the way that it's being expanded. Here's the global warming again. Let's look now at another thing. I'm somewhat infamous for this because although I'm worried about global warming, this part of my presentation has now been widely grabbed. It appeared in Forbes magazine, and since then it's been picked up by almost everybody. Let's look at the last 12 years of global warming. That little part up there, I'm going to expand that to fill the whole screen. And here it is. That little part is that. This is global warming of the past 12 years. There hasn't been any. Warmest year on record is 1998. And there actually is a slight downward trend, about 0.1 degrees. Now, what would we have expected from the model? We would have expected 0.1 upwards. Tiny, almost hard to measure. This could easily be a fluctuation. Look how these things shoot up and down from volcanic eruptions, changes in the sun that we don't fully understand. You have to look for the trend line. So you will hear a lot of people saying now, thanks to me, that there's been no global warming in the last 12 years, but it doesn't mean we shouldn't be worried. What worries me most is the fact that the 0.8 degrees is very close to the 1 degree that was predicted back in 1896. So what can we do about it? Are we going to run out of fossil fuels? Maybe that'll solve the problem. Well, actually, here's the fossil fuels of various countries. This is oil reserves, and there is Saudi Arabia standing proudly above the poor US. So there's our problem. What country comes in second? A lot of people are surprised to discover that number 2 country is not Iran, but Canada. Except if you go back a few months ago, Canada wasn't even on the chart. Why is that? Because their oil is coming from oil sands. It takes $60 a barrel to extract it. Whenever the price drops below $60 a barrel, they're losing money on every barrel. So it's extremely sensitive to price. But this is just the oil. What if we include in coal and natural gas? What happens? Let me put those on this plot. And they unfortunately go off scale, so let me change the scale, and there we are. Here's the United States. That's U.S. coal. And this is the shale oil. And there is poor little Saudi Arabia way down there. Here's Russia and China and Australia and India. These are the countries, especially the Russia, China, and India. These are countries that have developing economies, and they're not going to run out of coal very quickly. And China is building 1 new gigawatt, read big, 1 new gigawatt of electricity from coal every week. This is enormous. Many people are really excited and happy to see the economy of China booming. China is worried that its economy is going to drop below 8% this year. They're projecting 8% growth. Well, we are in a decline. They're growing still, and their energy use is keeping pace with that, mostly coal, and they're producing carbon dioxide. Take a look at the carbon dioxide production. Here's the US above everybody else. See that? We produce 1/4 of the carbon dioxide so far, responsible for 0.1 Celsius of global warming. We are the bad guys, 0.1 degrees Celsius. But you'll notice some of the developing countries have taken off, mostly China. Last year, 2 years ago, China surpassed the United States, continues to grow. It's reflecting their economy. It's the fact that there's a close correlation between the wealth per person and the energy use per person. We're on this diagonal. We have a lot of wealth, and we use a lot of energy. And here's China. Compare the wealth of China to the wealth of the US per person. And China is moving up that trajectory. And they're going to be, India, Russia, Malaysia, Brazil, they're going to be, I mean, the good news about global warming, when you see these projections of how bad it's going to be, the good news is that's reflecting enormous growth of wealth in the developing world. They don't like to say that because that insults the Chinese. The Chinese are very sensitive to that. But you need to know that. But this is also good news here. This is a measure of inefficiency. Oh, I better finish. Inefficiency. The least efficient countries in the world are China and India, and the US is actually pretty good. France is better. They don't produce much in the way of greenhouse gases because they're mostly nuclear. These are projections for Chinese growth. Let me just skip over those. Energy that we use drops as we develop. This is from 1850 till now. The US efficiency or inefficiency has dropped. So we expect that to happen with China and India. We got it. We got to go with that. This is an important plot. It was published by McKinsey, something that Art Rosenfeld here at Berkeley was ultimately responsible for. He should get a Nobel Peace Prize for his work in this. He then became the California Energy Commissioner, but he's still an emeritus professor here. And he did this work at Berkeley. Now McKinsey is publicizing it, and I think that's wonderful. What they're showing is if you want to cut out carbon, these are all the things you can do over here that earn you money. It's profitable carbon reduction. Most of this is you put some insulation in your house, and guess what? It's an investment. You pay less in energy bills. How long does it take you to return that investment? 3 years. People say 3 years, that's too much. 3 years for getting your original investment back? Even Madoff didn't offer that. And this is tax-free. And we're not talking about changing the thermostat to be less comfortable. Keep it wherever you want. If you like it at 75 degrees in your house, great, but put in some insulation. And you get this amazing payback. So this is a message. People, let me skip that. Cloud cover may kick in. I could talk about that, but I want to finish up. Notre Dame. This is a photograph of the Cathedral of Notre Dame. I took this photograph. These are the chandeliers. They used to be candles. You know what they have in there now? They don't have candles anymore. Compact fluorescent bulbs. Nobody notices. My house is all compact fluorescent bulbs. They're not what they were 5 years ago. They last long, they go on instantly, and they're really pretty. There's so much to be gained here. There are other options too. There's the supply side, wind power. See those two pictures? See that windmill? See the Statue of Liberty? Those two photos, they're not next to each other, but those two photos are to scale. That's the size of an 8-megawatt windmill in Germany. Solar is coming along. I'm very optimistic about solar. Right now, it works only because it's subsidized, but the price can come way down. I want to get to the questions. Nuclear is something that I believe the nuclear waste storage problem is not a real issue. If you read my book, you know why. It's mostly because the public is still scared about radioactivity and not scared about war in Iraq. The radioactivity is a much lower danger. There are things we can do. Clean coal no longer means coal without sulfur. It means coal without carbon dioxide. And that is realistic, and we're going to have to do that. We're going to have to do it cheaply so China can do it. This is a projection of a clean coal plant. Don't have time to talk about this. We need everything. We need conservation. We need clean coal. We need nuclear. Unless we get everything, we're not going to do it. We got to stop our green bickering. There are a whole bunch of technologies. I won't have time to talk about. This would be a good hour by itself. Let me just say, in summary, global warming is unfortunately going to come from the developing world. That's unfortunate because they feel they have the right to have as much power per person as we have. And they want us to pay for all the clean. We can't afford to, so there's a problem there. It's not good enough to set an example if they can't afford it. In our own country, please don't argue that compact fluorescent bulbs have minuscule amounts of mercury, and therefore we should be using light-emitting diodes. We bicker among ourselves to say, I am cleaner than thou, and it just does harm. We need everything, and in the end, I believe if clean energy is going to be sustainable, it has to be profitable. And that's what we need to be aiming for in our policy, if it's ever going to be used by China and India without us paying for it. So I'm somewhat optimistic. I'm always optimistic. This is a hard problem, and I don't see too many politicians actually addressing the fact publicly. So thank you very much. I'm happy to take some questions. Thank you. Here we have the microphone. If you have a question, we're happy to talk about anything.
How worried should we be about the Delta?
Very.
We live in
no,
Sacramento.
really, this is, I think, an extremely serious problem.
Yeah.
It's been a problem for a long time. And again, you get people bickering about it. Oh, they want to build the peripheral canal just because Southern California wants all of our water. I mean, Southern California gets all of our water. All of our water. We own it? No, but it's mostly for crops. 80% of the water goes for crops. That's what we're going to lose if the Delta collapses, which it could in a big earthquake. But with sea level rise, you won't even need that big earthquake. It's underwater. It's the New Orleans. I think that's the biggest concern that we should have in California right now. In fact, I tell people who say, oh, New Orleans, the government should have done something. They should have fixed that up. They should have sent billions of dollars. I say, oh, I'm glad you feel that way. Good. So the federal government, now you believe, should send billions of dollars to California to prevent this problem from happening. It's even worse because now these areas, what happens is they built these dikes to keep out the salt marshes, that water that was coming in, and they had the farm crops there. But what happens is that the delta evaporates, and so it's way below sea level now. And they have the dikes just to keep out sea level. So it's below sea level. It's the peat and the bogs just basically evaporated. So I think it's the most serious problem in California today. And the solution, the peripheral canal, is not to stop this from collapsing, but it's to provide that water to the farms in the southern San Joaquin Valley that will be destroyed, that will not get any water if the delta collapses. Anyway.
Dr. Muller, in your book, you talk about governmental spending for weapon systems a little bit. Does the physics justify a future president spending money on things like anti-ballistic missile systems, Star Wars systems?
Well, the ABM system, many presidents want that because once you get into that position, you realize, you mean the only thing we can do if a large country like the Soviet Union were to attack us is a retaliation? The presidents feel very uncomfortable with that. I have always been in favor of research and development into ABM systems. There was a time when ABMs were considered a way to abrogate treaties with the Soviet Union. And that was a time when most academics jumped on the bandwagon. We should not have an ABM because the government, and particularly the Reagan administration, was using that as a way to abrogate the treaty. But that's no longer an issue. We're having an ABM now. It's supposed to protect us from North Korea. I've never believed it was designed for North Korea. I think it's a nice excuse to build up a system that might someday protect us against China. I don't see any real harm in building ABM systems now because they're not going to be used to abrogate the treaty. They don't work very well. They probably will not work very well for the foreseeable future. And advanced countries such as China can work around any system. It's easier to build an offensive system than a defensive system. You know, bulletproof vests are much harder to make work than bullets. But it's not a whole lot of harm. It was harmful back in the days when it was seen as a mechanism for abrogating the treaty. And these days, it's no big deal. It doesn't work. It probably won't for the foreseeable future. It's not a big waste of money compared to other things.
And you alluded earlier to the danger of radiation. And I remember in a previous talk, you described what the difference was between the radiation in Denver, Colorado, for example, and New Mexico. I think that's an important point when we talk about storing radioactive materials. Could you cover that again? Yeah,
let me give a few numbers on waste storage. Right now at Yucca Mountain, if you happen to live downstream from Yucca Mountain, the safety has to be such that if you get all of your water from groundwater, from a well, which is south of Yucca Mountain, right in where the underwater water flows, that you're not allowed to get more than 15 millirem a year from that groundwater. That is what the Yucca Mountain requirement is. You can ask, why is it that? But that 15 millirem. Now put that in perspective. If you go and live in Denver, you will get an excess radiation of 100 millirem per year just from the rocks of Denver. It doesn't come from the cosmic rays, it's mostly from the granite. 100 millirem, that's in Denver. What is the largest dose that you are allowed to get as a citizen in any area? Well, they chose it to be the level at Denver, so we don't have to evacuate it. But if you had 150 millirem in Berkeley, we'd all have to evacuate, even though you get 100 extra in Denver, because of the panic and because that exceeds the limit. These limits are set excruciatingly low, and they're done that way partly because the people who worked at Yucca Mountain, the designers said, look, we can reach 15 millirem, so that's okay, we can do that. So they say, okay, that's what you got to do. But it makes people think that 15 millirem is dangerous. And so it doesn't work. If you say, oh, we can get down to 1 millirem, then people will say, oh, God, 1 millirem must be dangerous. Here's, to put it in perspective, if you get 1 rem, 1,000 millirem, your chance of cancer will increase by 1 part in 2,500. Your chance of cancer, instead of being 20%, let's say it was evenly 20%, about 28% of us die of cancer, would be 20.004%. That's with 1 rem. That's with 1,000 millirem. And you're not allowed 15 millirem if you live nearby Yucca Mountain. Anyway, there's a long story on the radioactivity. Mostly people are still frightened of radioactivity, and it doesn't help that we have one populist senator who happens to be the majority leader who gets reelected every year because he scares his state about nuclear waste.
Okay,
that's the most political I'll get.
This will be the final question, but Professor Muller will be joining us at the tea, so
I'll be around for the
he'll
tea.
be around for questions.
I heard an interview yesterday with Buzz Aldrin in celebration of the 40th anniversary of our trip to the moon, and he was suggesting that we colonize Mars, and I wondered what your opinion was on it.
Well, I don't see any reason to colonize Mars. It's much, much easier, safer, and cheaper to colonize the South Pole. We're not running out of space. I don't know how many of you have been to Nevada lately, but it's a lot prettier than Mars and a lot easier. In fact, I would argue that it's easier to colonize the bottom of the ocean than to colonize Mars. Now, historically, people have colonized places either for, they're sent out to discover things like Columbus, hey, go discover a nice route to India, or they come to escape their governments. But nobody is going to colonize Mars to escape their government because it's going to cost hundreds of billions of trillions of dollars to do that. So, and you depend on your government to keep you alive. The population of the Earth is going to peak around 2050, according to everybody, including the UN. We are not running out of space. We may be running out of, hey, Berkeley type space, but the South Pole is a lot more benign than Mars. So no, we're not going to colonize Mars. There's no reason to. Silly. Okay? I'll be around at tea. Thank you. Okay.